Welcome back, everyone. We're continuing with the big LLM architecture comparison from Sebastian Raschka. So I believe this week we're going to start with the eighth model he compares here, which is Kimi, their K2 model. So just highlighting a couple things here. He mentions that one notable aspect is that they switched from Atom with weight decay, so from Atom W to the new muon optimizer. And can't remember if we talked about muon in this group. I think we did. Yeah, we spent some time talking about
we did.
Optimizers, and we looked at muon. And so here is the chart from the Kimi paper where they say there's no big vertical spikes, short spikes in the loss. And I'm not quite sure what Sebastian Raschka is saying about, hey, look, the OMO training curves look pretty good too. If you see the blue one, it's got these spikes, right, where there's this very short, large increase in the loss, but the orange does not seem to have it. So I haven't really thought about it enough to know what he's comparing. If I remember right, though, this OLMO 2 model is the one that had the normalization layers both before and after each attention and feed forward layer. So maybe that's another way to reduce some of these big spikes. But even without it, even with only, I believe Kimi is post norm, you can see they got rid of these spikes. So that's good. He also notes that as a MOE model, they went really, really big. So 1 trillion parameters. Most of these trillion are in the experts. So in fact, when you do a inference, when you do a forward pass, it's not. Does it say here how many are active? I think it says somewhere in the diagram here. But so the MLP, pretty standard looking.
8.
Comparing. Is that a question?
Kimi was 8 plus 8. Kimi was 8 plus 1 shared. It looks like. Experts.
No, that's way too few. So you can see here 384 experts.
Yeah, but the active, you asked the active ones?
Oh, sorry. Yeah. 1 shared plus 8. Yeah. So whatever that works out to. 8 out of 384. So 1/65th of the MLPs are active, approximately, something like that. Or if you count the 1 shared one, whatever, 1/60th or so. So, and then where does it say the intermediate hidden dimension is 2048? So these experts aren't necessarily any smaller than the DeepSeek V3 experts, even though there's like 50% more of them. And then, sorry, I said post. Yeah, so you can see this is pre-norm. So the normalization before the MLP, the normalization before the
MLA.
the attention, and they did use latent attention from the DeepSeek folks. So they've got a lot of heads, 64 heads, and the embedding dimension of 7,168 is not that wide, and 61 layers. So it does look like if you compare the DeepSeek architecture, V3 architecture, and the Kimi architecture, there's a lot of things that they kept the same. You can see, right? like the model dimension and the number of layers. So this is really was the blueprint they started with, and they made a few tweaks. So the big tweaks are more experts, fewer heads.
And muon.
And then muon for training. Yep.
Do you remember, can you scroll up just a second to the loss curve there for Kimmy on the top? Do you remember that there's an inflection point about 2/3 of the way across where it kind of the slope changes? Do you remember what triggered that, or what that was correlated with?
No, but there is something that they changed. I'm trying to remember what.
Yeah, I'm drawing a blank. I remember.
This is not a mystery. If you reread the paper, you'll see that at this point they.
Is it like the learning rate changed or something?
They changed the context window, or they changed the learning rate. I don't remember, but there was something. They explicitly changed.
Yeah.
I don't remember. Yeah. The training data, but this is not like, hey, we were just training it and this weird thing happened. It's like, no, this corresponds to a change in the recipe, for sure.
Yeah.
What else do they say? Yeah, so that's the main highlights. So you could say it's really a variant on the DeepSeek architecture. So probably the most notable thing that they did differently is muon as an optimizer. Otherwise, there's some slight differences, and they scaled it up, and so that's impressive. But it's not architecturally terribly different. DeepSeek did a lot in terms of trying to get experts that were used in common for a given token to be physically located on the same GPU. I haven't seen any other papers where people explicitly mentioned hard work to get those experts to all share the same physical GPU. So they might have done it, but I don't remember seeing that highlighted in the Kimmy paper. But DeepSeek definitely highlighted that in each of their papers, the V2 and the V3 papers.
You had seen these side by side. I didn't recall how similar they were in terms of so many architectural elements and hyperparameters. And the release was pretty close, right? So this isn't one. I mean, we knew about DeepSeek before Kimmy, but did Kimmy take the DeepSeek architecture and move it forward, or did?
No. DeepSeek V3 was like December of last year, and Kimmy was, I think, only 2 months ago or something. So DeepSeek definitely came first. And I can't remember, Kimmy may have even explicitly said in the paper that they used DeepSeek V3 as the starting point. So I don't think they're pretending, that they just came up with this on their own.
Okay.
So, but what this does mean, if you think about it in the bigger context, is, right, the blueprint here is DeepSeek. The blueprint isn't Llama or something like that. Mm-hmm. Right? Mm-hmm. So this is, you could say that the conventional wisdom for making a model that you think will be state-of-the-art performance is, obviously you need a lot of parameters, so they went to 1 trillion, and you do mixture of experts and have a lot of experts. Mixtral had like 8 total experts, whatever, right? Here you're seeing hundreds of experts. I think that's not new, but it's just sort of confirmation that this is the latest blueprint that everybody's starting from.
Mm-hmm.
If they didn't, if the if the Kimi did not team did not try to optimize the co-location of the experts on the GPUs, why did they increase the number of experts if that's going to spread the work out more and result in a more latency? Was there some rationale on performance or something?
I think the basic rationale is if you want to get better overall performance. So in training, that just looks like better perplexity, better loss, right? But hopefully you're hoping that equates to downstream better performance on math benchmarks, MMLU, whatnot, right? Then adding more MLPs is a way to make your model bigger. So I think that's the main reason for adding more experts. It's a fairly easy way to make the model bigger. As to the work to try to get them to co-locate, I think that's something that DeepSeek has expended a lot of energy trying to figure out. And my guess is that other people just don't have the bandwidth to assign engineers to that. It's hard enough to do everything else. So maybe
but
it would be nice to have.
It would be nice to have, but the main objective is just to have better performance on the output of the LLMs in the field, as opposed to the training of the model.
So if I'm going to talk in business terms, okay, if they came out with Kimi K2 and the model was not as good at solving problems as Qwen or DeepSeek, then basically you're in the news for approximately 1 hour and then nobody remembers you, right? If Kimi can claim that they have better performance than DeepSeek or Qwen, then they're in the news, so they get the attention they want. If you don't collocate the experts, then that means that the inference has slightly more communication. It doesn't have any more flops, but it has more communication overhead. And the Kimi folks are probably not really in the business of inference. I mean, maybe someday they would hope to be, but I think from a business perspective, if you are trying to get noticed, you're probably better optimizing for good benchmarks than you are optimizing for save whatever 5% of communication overhead during inference. If that helps.
Makes sense. Thank you.
Yeah. All right. Anything else before we move on? All right. Next is GPT-OSS. I am very conflicted. I don't know what to think about GPT-OSS. One way of thinking about GPT-OSS is some of the things done in this model, OpenAI likely put them in this model because that's what they do in their proprietary GPT-4, GPT-5 models. We know that GPT-OSS is not as good as GPT-4. And it's debatable whether GPT-OSS is even that good within its weight class. So compared to other models that are similar to 20B, 120B. So I think we can talk about the architecture, but I'm always a little bit conflicted when, if they do something differently, is that necessarily a good thing? All right, so just super quick high level, if you look, you can see here, they're doing mixture of experts, but this is fewer. So in the small model, they've got 32 experts. It's debatable to me, the benefits, I've talked about this before, of doing MOE on a small model. It does increase the amount of GPU memory you need. And so it makes it harder to fit a model relative to a dense model on like a single GPU. But it probably does speed up inference slightly, so that's the trade-off. Otherwise, you can see the bigger model, they did actually get to like over 100, so it's not quite as many experts, but it's sort of this generally same architecture in terms of mixture of experts, pre-norm, the embedding dimension on this, these are smaller models, but if you look, the embedding dimension on this is a little surprisingly small to me at 2800. I think that's probably gonna restrict the performance of these models a little.
Even on the 120B.
Yeah, the 120B, this is pretty small.
Mm-hmm.
Why do you think that decision was made?
I don't know. I mean, it takes a while to plan and then train these things. And so this is why I'm conflicted, because we know that OpenAI is looking at DeepSeek, Qwen, all these people making headlines. I don't think they released an open weight model out of the goodness of their heart. So they wanted a model so that in my opinion, so that OpenAI is in the conversation of companies producing open weight models. But they didn't want this OSS model to compete with their paid proprietary model. They didn't want it to compete with GPT-5. So it's not clear to me how much their heart was into making OSS a really great model. You know? So that's why I'm really conflicted about it.
Yeah.
All right. So
Definitely.
Sebastian, was there additional comment? Yeah?
No, I just agreed.
Okay.
They don't want to hand out the secret sauce. That's all.
Yeah, so exactly. So if there are things in OSS that are not in all these other open models that you see, OpenAI probably does not consider that super important secret sauce, or otherwise they would have pulled it out. So he says, looking at the figures, pretty similar compared to Qwen. And let's see here. We can see some slight difference in the number of heads. This is a lot fewer layers, too. This 20 billion is only 24 layers. I really feel like this 20B model is kind of hamstrung. Number of layers is less, the embedding dimension is less, it's just, yeah. But we will see coming up. Yeah, so Sebastian says, width versus depth. Okay. Oh, actually, here, so this at 2880 is actually wider than the Qwen 30 billion. So maybe 2800 is not that tiny. So he says it's actually a little bit wider than this small Qwen. But it's only 24 layers instead of 48. So a little bit wider and shorter. I don't know exactly how you maximize this, but an interesting thing is if you look at like CNNs, they got very deep, but you don't see 100 layer transformer, let alone 150 layer transformer. So there's clearly diminishing returns for going super deep in terms of the number of layers. Okay, fewer experts, yes. And then one of the main things that I've seen people talk about is that GPT-OSS has a way of dealing with attention sinks that we haven't seen a lot of other people implement. So I know Llama has a beginning of sequence token. And so that allows attention to go to just that one token instead of any of the actual meaningful tokens in your text. And so the way that OSS does things is it changes the softmax calculation, and they have this attention bias thing. I don't remember exactly what the calculation. I don't know if it shows it here. But basically, in your standard softmax, you exponentiate the dot products for all of your queries and keys, and then you sum them up on the bottom, and so they all add up to they have to all add up to 1. And so the attention weights for all of your real text tokens have to sum to 1. So one way you can have them not sum to 1 is like Llama, where you have a beginning of sequence token, and that can suck up as much as it wants. So if 0.9 goes there, then only 0.1 is distributed amongst all of your real text tokens. The other thing you can do is you can just change the calculation of the softmax, and you add this bias term so that they no longer have to sum to 1 anymore. I haven't seen, other than just people talking about the fact that OSS does it this way, I haven't necessarily seen. I don't know if any of you guys have heard people talk about whether or not this sounds like a better way or not of dealing with attention sinks. But that's the main thing that I saw that was different in OSS. And again, if this was like the key secret sauce that made GPT-5 great, I don't think they would have included it in their open weight model.
Ted, I'm sorry, I didn't follow how the bias changes, how it acts as a sink. Can you walk me through that?
So in the GPT-OSS implementation, attention sinks are not actual tokens in the input. Instead, they are learned per head bias logits that are appended to the attention scores. So basically, if you said, I've got 100 tokens in my context, and so, and we exponentiate all of them, and so we do all of those things, then that's the sum of all of those is what's in the denominator. And so
right.
If you these 100 individually, when you sum them up over that common denominator, they're going to add up to 1. But so the simplest thing you could do is then in the denominator, you say it's all 100 of these plus some learned number. Okay. And so if that number's positive, then all of your attention weights are no longer going to sum to 1. That's the gist. So I guess what's different about it is that it has the ability to learn different behavior so that it can situationally decide how much to let it not add up to 1 or to stick to traditional softmax where it all adds up to 1.
And so if I have a sink that I'm attending to, the output of the attention layer will be the value associated with that sink. Right?
Yeah.
A bias towards it, I mean.
And in concept, what you can do is, so let's take the llama case where you have a beginning of sequence token, okay?
Uh-huh.
You could have the values for the beginning of sequence token be all zeros.
Can we get, Harold, I think you're, can you mute, please? Thank you.
Yeah. So So the values for your beginning of sequence token hypothetically could be all zeros. And so then in that way you could ensure that anytime you attend to the beginning of sequence token, it has no effect on the residual stream because it's just all zeros.
Oh, okay. So the implication being that whatever you attend to at the attention sink, you expect it not to influence the residual stream.
Yeah, that's the intuition. That doesn't mean that's actually what happens, but that's the intuition. Okay.
And that's how a bias, because when you have a bias, you don't really have a value to associate with it. You just you downweight everything else, but there's not an attention value that's injected. Okay.
Yeah. So if all of your actual tokens had dot product exponentiated scores, let's say between 0 and 5, okay, and your bias term was 80 million, then basically effectively what you're saying is all my attention scores are close to 0 for every token. I don't have to attend to any of them. And so they don't have to have non-zero values, but they're just getting so downweighted by a very large bias.
Got it. Okay.
So it seems to me...
Would it ever make us... I was going to say, would it ever make sense to go the other direction? I understand downweighting everybody else, but what happens if it goes the other direction? It goes negative, I guess.
I don't remember the implementation. It may not be allowed to.
Okay.
But yeah, I mean, in theory, if it's negative, then you're attending to things more, which I don't know that
it seems like it.
Because you're already attending to things. So all you're doing is sort of scaling up the attention.
Right. Yeah.
But the main issue right now is that you can have sharp distribution, you can have a wide distribution, but you can't really have a zero distribution of attention.
Gotcha.
And so if you have an attention head that's just hypothetically looking for references of pronouns to the noun that came before it, the antecedent, and a sentence has no pronouns whatsoever, then that head, you theoretically would want it to do nothing. You'd want it to do a no-op. But with softmax, you cannot do a no-op. The attention weights have to add up to 1. So you either want to have a physical token that you attend to that you throw away, or you want to have some way for them to not sum up to 1. So it seems to me the benefit of this is that by being learned instead of a static bias. There was years ago, I forget the guy's name, who said, hey, just put a +1 in the denominator. And then if all of your attention weights are relatively small, then the 1 will dominate. But if your attention weights are all like 10, 20, 100, then the 1 is just a rounding error and it doesn't really matter. You can ignore it. Right.
So this is a learned value that I assume it's a product of the residual stream, learned, like a learned weight matrix, like the QKB.
Yeah, I forget. Does anybody else remember? I don't remember the exact way this bias is calculated. But you can see learned per head bias logits that are appended to the appended. So what, figure 31? I don't see where it's in this code.
Okay, I don't mean to take us down a rat hole.
Yeah. So it looks like maybe it's your actual attention weights, and then this is just a weight. It's a parameter. So it's just a scalar per. So then it's
kind of like really, 1. It's kind of like 1, except it's a learned.
Yeah, it's really just a +1, but you can change the 1 to something else. But it's not based on the hidden state or the input token. So basically,
that's too bad. I could see it having value if it was learned. If it had a weight matrix to calculate it, it kind of would allow the attention head to say, do I want to have a nothing, do a no-op or not?
Right. So if you learn a 0 here, then you're basically doing standard attention. And if you learn a larger number, then you're saying this is an attention head that sometimes does not want to attend to any of the tokens that came before it.
Yep. Yep. For all queries, for all keys.
Yep. And it's per head to decide whether you want this parameter to be 0 or non-zero. And I think you can do the same thing with the beginning of sequence token. If you just have your query and your key weight parameters so that the keys don't ever match with the beginning of sequence, then I think you can sort of force it to not have a sync. But obviously the model's able to learn a sync behavior when it wants to. And even before we had beginning of sequence tokens, it still learned how to do that. It's just, life is a lot simpler when you have an explicit someplace for it to do the sync. It doesn't have to waste its resources trying to figure out how to do that. All right. Any other questions? If not, we'll move on to the next model. All right. Grok. So this is the 2.5 version. I haven't played with, I don't remember reading too much about Grok 2.5. Sebastian says it looks fairly standard. So he's comparing Grok to Qwen. And you can see 270 billion. This is in the large but not crazy heavyweight sized model. So let's take a quick peek here. Small number of experts, only 8. So this is like Mixtral. Embedding dimension is large. It's 8,000. It's 64 layers. So compared to Qwen, it's wider, but not as deep. Qwen is a little bit narrower and deeper and obviously more heavily MOE. I would say that's just at first blush the biggest difference.
What's this dense plus MOE? Do they alternate layers?
On Qwen or
Qwen's on the left, right? Grok's on the left. Now on the Grok they have a dense next to the MOE. I'm just wondering if they alternate layers or how they did that.
Where does it say? Oh,
Dense feed forward.
I don't remember. Let me see if he says here. Small number of larger experts is an older trend. So here is the use of what amounts to a shared expert. The additional dense expert is always on. So here in Qwen, you have one expert that's always on and 8 out of 128 to choose from for each token. But this dense thing is slightly different sized than just this shared expert here. So it is a little different. But fundamentally, it acts like a beefier shared expert, I guess.
Okay. At every layer.
As far as I can tell, it's every layer, yeah.
Oh, I see.
Anybody
I see.
here?
It's a large. So it's the intermediate, the kind of the internal to the MLP. That's the layer that's larger for the dense. Huh? 32K instead of 16K in the middle.
Yeah, and it could have been smaller. It could have been anything, right? You can. There's nothing that says your shared experts have to be the same size as your, right? If you think
as long
that
as
there's
the hidden state.
Yeah, as long as if you think there's a lot of stuff that people want to share, you might have multiple and or bigger shared experts than.
Yep. Yeah, that was what I was wondering is why would you make that choice instead of multiple shared? Is there some advantage to a wider one? Wasn't immediately obvious to me.
Yeah. Yeah, I'm not sure
I guess
either.
I guess a wider one must be, there's more parameters there, so it must be more expressive. Because if you
I mean,
have
if you
multiple shared, that's kind of like a block diagonal almost, isn't it?
if you think about it, right? If you had two low rank things or one high rank thing that's double the rank, right?
Mm-hmm.
You probably can get a lot of overlap, but at the end of the day, if you think about like if you have, you know, two 10 by 10 matrices versus a 20 by 20 matrix, right?
Mm-hmm.
You probably can do sort of roughly the equivalent of like a block diagonal, but you're not necessarily getting those off
Right.
diagonal entries. But
Yep.
a full 20 by 20, you can get every possible relationship. That'd be my guess.
Yep, that makes sense.
Anybody here played with Grok 2.5? Warren or anybody, do you have any comments on, is it even something terribly interesting for people to check out, or is it just sort of like a footnote, it exists?
Yeah, I think we're up to Grok 4 by now, and I really have not been paying attention to the Grok series, so I would say probably like a it exists footnote is appropriate.
Yeah, I used it. It was on X2. It was never good. They didn't make it until Grok 3.
Okay, good. Thanks, guys. All right, next, GLM 4.5. I don't know a lot about GLM 4.5. So we've got instruction reasoning hybrid similar to Qwen 3. So here on these benchmarks, you can see the bigger GLM, the smaller GLM Air, and they've got, you know, O3, Grok 4, Claude 4 Opus, a bunch of heavyweight models on here. Here's the Qwen 3 Thinking, Kimi K2, and then some other things, agentic reasoning coding. So the flagship is 355 billion parameters, and supposedly outperforms Claude 4 Opus on a bunch of these benchmarks. Slightly behind O3 and Grok 4. And then their smaller 4.5 Air is 106 billion parameters. That is pretty close to their full-sized model. So let's take a quick peek at the architecture. It's mixture of experts, not quite as many as we see in some of the Chinese labs. Qwen and, you know, Kimi. Otherwise, pre-norm, kind of deep, 94 layers. But the recipe seems pretty similar to Qwen. They say GLM does have the shared expert that DeepSeek has that Qwen 3 doesn't have, but that shared expert may come back depending on, we'll see in the future. And they say GLM 4.5 does use this attention bias mechanism. He says used in GPT-2 and GPT-OSS. I do not remember GPT-2 having an attention bias mechanism. Any comments or questions about GLM? All right, so then we have an addendum. This was not part of the original blog, but he added here Qwen 3 next. So in this figure, we've got the Qwen 3 next 80 billion total, active 3 billion. So that's a very small number of active, and this whole instruct thinking variant stuff. So it's 3 times smaller than the 235 active 22. Introduces 4 times as many experts and even adds a shared expert. So let's take a quick peek. So totally cranking up the number of experts, and 4 times as many experts, but you can see they went from 8 active to 10 active. So they're not cranking up the number of active that much, but it's just in terms of whatever. So here's where you can have a lot of capacity, but still have very fast inference because most of these experts are not used in any one given forward pass. The other way they shrunk it, you can see, is it's half the layers. It went from 94 to 48. Smaller model dimension. So what else does he say? So gated delta net, gated attention hybrid. So in this model, they replaced the regular attention mechanism by a gated delta net plus gated attention hybrid, which helps enable the native 262K token context length in terms of memory usage. How does this new attention hybrid work? Compared to grouped query attention, GQA, which is still pretty standard, their hybrid mechanism mixes gated attention blocks with several gated delta net blocks in a 1:3 ratio as shown in figure 36. So here's where you normally have regular attention. And this gated delta net controls this whole business over here on the right. And then we got 3 of these, and we've got 1 regular attention here with the gating on the left. So I haven't read, I don't know if any of you guys have read about Qwen 3 next. I'm wondering if this is really sort of 4 layers. There have been some papers, that say that in theory, you don't necessarily need to alternate attention and MLP layers, and they don't have to be equal numbers. So there have been some a few experiments that said, like, hey, you could actually, instead of having a 36 layer model that has exactly 72 layers, 36 attention, 32 MLPs alternating, you could do something like start with 5 attention layers, then have a bunch of MLPs, skipping the attention or whatever, and then at the end, make sure you have a bunch of attention layers, stuff like that. But this seems like this would be a pretty significant departure if you're cranking up the amount of compute in these so-called attention layers, as opposed to the the MLP layers. Let me see what else he says. We can think of the gated attention block as a standard scaled dot product attention that can be used in GQA, but has a few tweaks. The main differences are an output gate that scales the attention result before is added back to the residual. So that just means that we can sort of attenuate the signal, so you can proportionally quiet the attention. Zero-centered RMS norm for QK norm rather than standard. That's normalization, not really that. Hey, Roger, my favorite thing, partial rope, doing a subset of dimensions instead of wasting your energy doing rope on every dimension. So that's how the attention part is changed. So mostly it looks like it's the same, other than the output of attention can either, normally it just is forced to be written to the residual stream. Now you actually have a volume knob where you can turn it down. The gated delta net is more significant change. In the delta net block, QKV and two gates, alpha and beta, are produced by linear and lightweight convolutional layers with normalization, and the layer replaces attention with a fast weight delta rule update. However, the trade-off is that DeltaNet offers less precise content-based retrieval than full attention, which is why one gated attention layer remains. Given that attention grows quadratically, the DeltaNet component was added to help with memory efficiency. The linear time cache-free family. The DeltaNet block is essentially an alternative to Mamba. Mamba keeps the state, blah, 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 state space. DeltaNet keeps fast weight, da, da, da. So the way I'm going to read this then is that if the model has 48 layers, then it has 3 cheap ones, 1 full attention, 3 cheap, 1 full, and 48 of these total. So the first 3 layers are delta layers. The 4th layer is in a full regular attention. Well, not a layer, but a gated attention layer. And then the 8th is a gated, and the 12th, and all the way up through the 48th. So I think that this is not extra compute, but rather this is meant to signify it's 4 times 12, 48 total layers. So every 4 you get 3 of these and 1 of these. Does that seem like the right way to read this?
Yeah, kind of the macro level, that seems right. I'm still not, I didn't read ahead, so I'm still not clear exactly what's going on with this gated delta rule and the alpha and beta and using a conv instead of a weight matrix there. Does the conv imply that it's kind of a sliding window?
I don't know exactly what it's doing, but Sebastian is pointing to all of these alternatives to full attention. Mamba, any other like linear attention, what they're trying to avoid is having a full KV cache of every token that ever came before, and then doing an expensive quadratic calculation on the full length of that. So I suspect with these convs, you're basically getting a windowed thing.
Yeah, that's
right?
what it sounds like, yeah.
Yeah. So if your conv is size 16, then effectively you only need to keep the last 16 tokens instead of every token you've ever seen.
Yeah.
So the idea would then be you can do local attention of, and maybe not as perfectly as windowed attention, but you can do almost as good local attention on the last 16 tokens. And but there are times when you really need attention to go and pull something from longer ago. So every 4th layer, you pay the full cost.
Which seems reasonable. I mean, you're doing those sliding window things for computational efficiency. So you're giving up something for that efficiency. To be able to just sprinkle in a little bit of full attention seems reasonable.
Yeah, and I forget what we're looking at. Was it Gemini or whatever, where they did some cheaper attention like half the time or something like that. And then ultimately they cranked it up to 3/4 of the time because they're like, yeah, you really don't need global attention that often. So
Right. Yeah.
This seems to be yet another lab that said we can get away with global attention 1/4 of the time. So whether you do Mamba or this Delta thing or whatever, you do something else. Windowed, sparse, linear transformer, whatever you do, the idea is this is not zero cost, but if you had really, really long context, like 100,000, 300,000, then you could sort of say that this is cutting your attention cost in 1/4 because this is going to be constant and this is going to scale with the length.
Yep.
It's not quite, true, but conceptually, for super long context, you're cutting your attention costs into 1/4.
Yep.
So I don't know if there's a paper we might want to read the Qwen Next paper and get a little more details.
Yeah,
on what they're doing.
I think
here.
I'm interested in understanding what that gated delta rule is. So I'll take that offline if it looks interesting enough to expand, and we can pull in a session on that.
Cool. Thanks.
Or maybe squeeze it in as a small piece.
All right. The other thing we see in this Qwen Next model is multi-token prediction. So let's see how they implemented it. Trains the LLM to predict several future tokens instead of one at a time. Small extra heads output logits for the token after, up through however many K. So this looks like these are lightweight prediction heads. And we sum the cross-entropy losses for these. This additional signal speeds up training, and inference may remain one token at a time. However, the extra tokens can be used in speculative decoding. And they say which Qwen 3 Next does seem to actually use speculative decoding. So it not only yields a multi-token prediction module with a high acceptance rate. So acceptance rate is the right. That's the rate that when you do speculative decoding, that your initial guess for the next token is correct. So if your guess acceptance rate is 100%, then your speculative decoding dramatically speeds up inference, because if you predict 4 tokens at a time and you had 100% acceptance rate, you're only doing inference 1/4 of the time. If your acceptance rate goes down to 0, then basically you have no speed up whatsoever and a slight overhead for whatever your speculative predictions, whatever the cost of those predictions are. So Qwen 3 Next specifically optimizes the multi-step inference performance, further improving the acceptance rate of speculative decoding in real scenarios through multi-step training that maintains consistency between training and inference. So what they're saying is that the original speculative decoding paper says you can use a smaller model, and then you sort of hope, if the model's in the same family, trained on similar pre-training data, that it will make similar-ish predictions such that the acceptance rate is relatively high. And I guess the Qwen 3 Next, what the scientists are saying is that by having this sort of natively in there, the way they trained it, the acceptance rate is higher because the model sort of knew about this multi-token prediction in the way it was built, rather than you just slamming on some small model and having it try to guess right for the big model.
And this extra head, it comes off like the logits or something like that, just before the top end. Or I guess it'd be before the logits, but.
So basically, in a regular LLM, you have your tokens and you embed them, and then you do layer, 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 layer one more RMS norm, and then you just have a linear layer that if your vocabulary size is whatever 200,000, then this linear layer has 200,000 logits that you softmax. I think from that paragraph, Sebastian's saying you just have a second linear layer here that instead of predicting the next token, predicts the +2
next
token,
+1,
and the +3 and the +4, however many. If k equals 4, then you're basically saying next and 3 more. But that because it was part of the way the model was trained, they're saying that these prediction of the second next, third next, fourth next have higher acceptance rate. Their guesses are right a lot of the time compared to if you just said, oh, let me take a small model. Let me take a 2 billion model. Also, the cost of doing a guess is relatively cheap. It's just this big fat decoding layer.
That's not novel to this, is it? That we've seen that before, haven't we?
Trying to remember which one it was.
I thought even DeepSeek was doing.
One of the DeepSeek models had multi-token prediction, but it was heavier weight. It had some kind of like attention layer and thing. And
it was recursive, yeah.
And the purpose of that was to speed training. They never actually bothered to use it for speculative decoding.
Right.
So you could see that they weren't all that interested in it. This one is lighter weight, which seems a better fit for actual inference speculative decoding. And they, the comment is that it speeds up training. How much did it actually speed up training? Not clear. If it was a lot or a little bit. Any other comments or questions about the Qwen Next? So pretty cool. So Warren started us off. 3 total sessions. Warren did the first 2. And we started up top. And so what did we see? So reducing the KV cache, you can get rid of some of your attention layers. You can use multi-head latent attention to compress them, or you can do group query, typically with a factor of 2, that cuts the size of your KV cache in half. We see again, for a laptop or a single PC, it's debatable the value of a mixture of experts. Maybe it gets you slightly faster inference, but for state-of-the-art models, it looks like many large mixture of experts is the current conventional wisdom. And then in terms of normalizations, most of the models, say 80% of them, are pre-norm. Olmo did pre and post, and there was like one model in here that did post. I don't really know this QK norm. But the idea is, I think we mentioned this in one of the meetings. It's like the normalization may mess with your mathematical properties of like convergence of gradient descent and all that. But people are just like, well, we don't really care. We just want to make sure we don't ever get like overflows or anything in our floating point. And so voila, you normalize stuff over and over and over again. And if it's in some way affecting your calculations, through its training, the model learns to compensate for the ways in which you are, hurting its calculations. So it's a similar thing here where you just make sure that your queries and your keys can't get abnormally large, and you normalize there. Sliding window attention is another way to reduce your KV cache cost. I don't think it's terribly popular. We'll see if anybody else latches onto that. And then again, more small experts. To make things even cheaper, this small LM did no positionally no positional embeddings, I think, every other layer. Oh no, actually, it's not even that much. They did no positional embeddings every fourth layer. So how much can you really save by doing rope 3/4 of the time and then nothing 1/4 of the time? But this is meant to be for a really small model, 3 billion. So they squeezed a tiny bit out of it for that. Yeah. And then we get to the ones we talked about today. So obviously little differences. Some people are going a little wider in the model dimension. We didn't really look at it, but in some cases the MLPs were slightly wider, narrower in the hidden dimension. But there is, at the moment, a conventional wisdom that seems to have converged in terms of, at the frontier, super large number of parameters, use mixture of experts, many small ones. I think the Western labs haven't necessarily caught up, but it certainly looks like all the Chinese labs are in agreement that many small experts is the way to go. Whether or not to have a shared expert, the jury's still out. But yeah, so Sebastian did a really good job, and hopefully this was helpful just in terms of understanding what are the slight differences, different choices that people are making right now in the really high performant models. I think we'll still see other models that don't necessarily follow that recipe if people are building smaller, more specialized models. But mostly here he's talking about these models that are really pushing the envelope. Anything else we want to talk about our cover today?
I wonder if anybody's run llama Cloud, in specific, like your own model.
I haven't. Anybody else?
I've run it on desktop, not cloud, but llama. Or
I think it'd be like probably the most convenient way, if you can run your own models, is to do it through, it's like a $20 llama Cloud thing they have now.
So can you explain how that works, Kevin?
I'll put a link in the chat. It's pretty simple. And I know for sure you can run the top models. I can't see on this webpage if you can run your own. If you can run your own, that would be sweet for $20. And I can ask ChatGPT if that's the case. And I mean the models that you upload to Hugging Face.
So basically, you've got a llama on your computer, and it makes an API call, and the model's actually running in the cloud somewhere.
Yeah, I mean, it partially solves the hardware problem. If you can run it, I'm asking ChatGPT right now.
it would be faster than running it on your own machine.
In a perfect world, it would be cheaper than provisioning your own cloud GPU to run the model.
It says not yet. Currently in preview, you could do the OSS 120B, Qwen 340B. But my guess is that, because it's in beta, my guess is that you could probably access your Hugging Face models. I don't see why not.
I think it's just the models they have pre-installed. I don't think you can pick your own.
Yeah, at this point, yeah.
Yeah. So I'm a little bit pessimistic. I think that it's going to be the same experience that people have right now with like Claude, whatever, right? $20 sounds really great, and then at some point they're going to start capping tokens just because you can't give away compute for free, unlimited compute for free. Well, not for free, but you can't give away unlimited compute for $20.
Yeah, this is kind of an area that I've had questions about when you're off using, Claude or whatever, using these models. Like, how much resource am I really using up? How much, like, I see these big AI farms that are taking megawatts and I think it's up like a gigawatt, right? For some of these larger AI farms. How much energy am I burning? Is it, per individual, is it really that much? Or does it compare to my light bulb? It's just that we've got 100,000 people with light bulbs on their desk. You know what I mean?
OpenAI,
Like,
well,
I
OpenAI does
do.
extensive work with that. Like they'll compare it to the cost of creating a hamburger, that it's just pennies compared to other luxuries that we have.
Yeah, I was going to say, I do dinky queries, right? So, like, I'll read a paper and I'll say, hey, I don't understand this delta rule thing, right? So I ask, the LLM about delta rule. And that's like dinky. But I think it's people like Warren who, have code bases. And so now you're trying to give it tens of thousands of tokens that's just the existing files. And you're saying, hey, I want you to refactor this or write this new module that works with these existing functions and classes. When you have these long contexts and you're doing a bunch of thinking tokens, then I think that's where you start really racking up the electricity.
I don't have a gut feeling though, an intuition though, about how much that really represents. Even Warren as a power user, is he equivalent to what? Is that the same as a space heater? And if that's doing the work of three other developers, how does it compare to the energy footprint of the three other developers?
Humans are expensive. Tokens are not.
That's kind of, yeah. Even though I feel guilty about the gigawatts spent on a new AI farm or whatever you're calling these things, I'm kind of suspicious that it's relative to the people, it's pretty cheap.
Yeah, they were saying
And
for
relative.
they were saying for a $200 pro that they're spending over $1,000. Like they just lose all this money to get more users.
That's OpenAI saying that?
Yeah, I mean, I think that's all of them. They're all trying to get more users, and that like the VC
Well,
will
we're getting
pick up the
we're
funds.
getting a lot of the Chinese ones that are claiming a lot better efficiency than OpenAI, aren't they? So if it's $1,000 and some of the claims weren't, I'm trying to remember when we were reading through like the DeepSeek, wasn't it like 40 times cheaper? So that's a pretty small number.
Yeah, I mean, they get their inference parameters down, so it's not as much as running like a full old Llama 405B,
Right.
something like that. But yeah, if you could do this in the future, the old Llama Cloud with specific models, I understand like a specific task that you need done, and that would be useful. And you could like the Deep Infra and Together AI and all these others, some of them you can give them your model and then just run it through inferencing, and it's low cost compared to most of the proprietary models.
Well, and I think one of the main things is low headache, right? So if they're charging you per token, you don't have, if you were manually provisioning, you'd have to worry about spinning up, spinning down, all that stuff when you weren't using it. But if they charge you per token, then, they're just helping sort of timeshare, to use the old term, timeshare you and all the other people that want to use a particular model. And you don't have any of the headaches.
I posted the link.
I'm still hoping. Go ahead, Alfonso. Sorry.
All right. I posted a link of the guy who runs the T3 chat, the AI service, $8 a month, and he talks about the costs and how they're going. and how they're computed. It's a lot more than he had expected, and he estimates that he can only, even if he moved out of San Francisco, the cost would only half of what it currently is. So, yeah, like Ted says, I don't foresee this to be a long-term pricing stability issue. This is strictly attempting to outlast the competition and hope that you'll be able to raise prices afterwards.
Right. Grab market share while you have investor money to burn and hope you outlast the competition before you have to raise your prices or cap your tokens too dramatically.
Yeah, and OpenAI just got another 500 billion, right? So
that's a lot of money.
It does seem like there's
with Oracle, and then another 100 billion with NVIDIA, and then there was another 100 million with Databricks. So it's good news for some.
No, but just this week, I think they just raised another 500 billion on the stock market. So, through not through equity, but through some other financing.
All right. Well, I'm looking at the time. Do we want to wrap up the conversation here and then maybe have a quick conversation about what we want to do next week?
Sure.
All right. So you can stop the recording. I hope Jerry was recording. I don't know. Maybe we weren't recording this one. That would be terrible.
I heard it when the recording started, so I don't know if it has lasted until now.
He said,
all right. Yeah, Jerry said
and I
talked. Recording, so.
Oh, he's got to record by his icon, his participant list, so I think he's good. He maybe just stepped out for a second or something. All so right. He has to edit this out then.
His problem. Roger, any thoughts about next week?
No, you had posted a bunch of interesting topics, several of which, you created a list. We could copy that over to the general agenda.
Was VLLM one of the other ones that you were more interested in?
Yeah, there was a VLLM blog about how VLLM works. There was also another one that caught my eye, which was the coding up a small custom CUDA kernel. That sounded pretty interesting.
And just for the record, I was not planning to invent a session for that. I was planning to just look at somebody who's published a tutorial that says, here's how you can, write a small CUDA kernel, and then we all can just follow along and do it.
Oh, see, I was wanting to create something.
No, I want to create something, but I'm saying, but the instructions for how to do it, I was not saying I was going to create those instructions. Yeah. I was just going to find somebody who had posted how to do this.
Yeah.
All right.
I think that could be fun. So I can volunteer for a few of these, but I'm going to have a hard time next week, and I think the week after. I'm not sure that I can present those 2 weeks. So I could queue up for, let's say the VLLM is probably the easiest one because it's just going to be reading through and providing, just leading the discussion. The CUDA might take a little longer because, like I said, I'd kind of like to try coming up with something and actually creating it.
Well, I see that Nina has her hand raised, so I'm excited. Do you have an idea?
Yeah, I was going to volunteer for VLLM stuff maybe 2 weeks from today, but if Roger, you're doing it, it's I don't mind. Yeah, that's okay.
No. If you're interested in that, please go ahead and do that. And then I'll try to get the background work done on the CUDA stuff. and
And
I'll
just so you
follow you
guys
on that.
know, I'm putting in chat. So our friend Alexa, who used to be a YouTuber, I mean, technically he still is, but he doesn't post like he used to. But he was doing, for his work, he had to do a bunch of stuff with VLM, and so he decided to document everything he was learning about how VLM works under the hood. And so that was what I had shared with Roger. So you absolutely don't have to follow his
Mm-hmm.
outline, but it's a good resource.
Got it. Yeah.
So I just put that in the chat. Obviously, because of the V for virtual, one of the big things that VLM does is paged attention. That's an interesting concept that they have, and I'm very curious if Alexa or anybody else talks about how far they go with paged attention, because in the paged attention paper, they say there's all kinds of things you can do with paged attention. Okay? They're like, you can do beam searches, you can do all these things. But just because they say you can, I don't know that they actually do any of those things, because it may not be all that practical. So, but VLM is very cool. And then very standard inference things. So if you guys are not familiar with chunked prefill and balancing prefill and decoding on each GPU, those are techniques that are pretty widespread. I would say that VLM is close to the frontier in terms of throwing in all the best tricks into their bag of tricks. I think a lot of people use VLM for fast inference.
Cool. So,
All right.
Neha, you had said a couple weeks for you
Yeah,
on that.
maybe 16th. Yeah, 16th October.
Okay.
Yeah.
So
Okay.
then
Yeah.
we
And
just
maybe I can
need
follow up there.
something for next week. We did move on.
I hadn't looked over previous meetings since I just joined this past month. Has there, but I didn't see anything about developing models for coding, the programming type stuff, primarily. So I was curious if you recollect having any meetings on those in the past, or preferred models or anything like that.
We had Warren had done some, and we had a couple sessions, I think, where there was a fair amount of discussion about using LLMs for coding and how you would do that. So if you're talking about using the models or like creating and defining, training a model, which one?
Yeah, training.
Yeah, we haven't dived.
I
I don't think we've dived into that. Is that something you're interested in or something you're familiar with?
Yes, I am. I'm doing some experimentation with the training models, but my hardware is much older, and so I was looking for something that might help me be a little more
Yeah,
effective and practical with my hardware.
Yeah, you don't use your own hardware, just use cloud stuff. Kaggle will give you a bunch of free compute, and then Colab has a good free tier. And then if you need to go farther than that, I know Google Cloud will just hand you $300 in credits if you want to use Vertex or TPUs. And then, yeah, I think I have a list somewhere of like all the places you can squeeze free compute out of. But yeah, I would not try to run stuff on your own hardware unless you like that's specifically why you want to do it.
So for
Okay.
what it's worth, if we as a group collectively are kind of aligned on a project that we want to do, I have an angle for potentially getting us compute for that.
Yeah, my
But
two projects on my, I have plenty of projects on my list. So if we,
yeah, no, I'm sure there are plenty of people who have plenty of projects. So I'm saying I'm not saying I can get blanket, you know,
um,
but that's why I'm saying sort of if as a group we collectively are aligned, like this is a really interesting project that more than one person is interested in, then I think I have an angle to get us compute.
I have, well, yes, my two candidates, and like I'm gonna see if I can track down compute for them. But one of them is like more or less like a modular inference engine. The idea being I grab like multi-decode and then like everything else I could find related to that, Polaris, head infer, etc. And I was gonna try and set something up where for a given coding task, let's see if we can use like a model optimizations kind of router and then learn what the most effective optimization series is for that given task. Is my that I have spec'd out, but not I have a little bit of code for that, but not a ton. And then the other one I have is there's a paper called RPG, which was very interesting to me. The repository planning graph, the idea being they want to be able to basically like one shot generate entire repos that function. And so I have a plan to implement that and see if I can verify their results.
Okay, well, if you're willing to have those be sort of West Coast ML projects, then I think if we can discuss those and then write it up, and if you have a sense for ballpark what kind of compute it would take, then basically I can run these proposals by my contact at RunPod and see if I can get us some kind of.
Yeah, I would be quite, yeah, well, especially because multi-decode, has West Coast ML